Imagine you wake up floating in space. No ship, no planet, just you and the stars, and the sun glinting off your helmet. But where are you? In which way is, well, up or down? You know there's the sun, but what's exactly your position in the solar system? To the left, above, or below? Very soon these earthly words just lose meaning here. But we, humans, desperately need orientation. And believe it or not, astronomers found ways to give it to us even in the depths of space. So here are the questions we're chasing today. What's above and below the solar system and what it even means? Are we left or right in our own galaxy? And what about its universal position? And overall, can we actually find directions in space? And what does it reveal about how the universe is built? So let's start where it all makes sense, at home. Here on Earth, down is obvious. It's the direction gravity pulls you. Drop something, and it falls toward the center of the planet. That's our built-in orientation system. From there, up is just the opposite. Away from Earth's center, simple enough, until you try to aim a telescope or launch a satellite. Then suddenly, up and down change dramatically each and every minute because of Earth's movement. So we add a new layer, Earth's rotation axis, the imaginary line that runs from the North Pole to the South Pole. That axis gives us a stable reference point, one that keeps pointing in the same direction no matter where you are on the globe. And that's how we get true north. Extend it far out into space, and you'll find Polaris, the North Star, sitting almost perfectly above the pole. Not directly above, but so close that it barely wobbles. Hikers, sailors, ancient civilizations, they all used Polaris to figure out where they were going. But this particular star hasn't always been the North Star, and it won't be forever. The reason is a slow cosmic wobble called axial precession. It takes about 26,000 years to complete one full wobble. And because of that, the point in the sky our axis points to gradually changes over millennia. About 5,000 years ago, the North Star was a different star entirely, Thuban, in the constellation Draco. And in about 12,000 years, the title will pass to Vega, one of the brightest stars in the night sky today, but nowhere near the pole right now. That's how our planet's up changes, in the blink of an eye by universe's standards. In the southern sky, things get trickier. Sigma Octantis is the South Pole's counterpart, but it's so dim you can barely see it without a telescope. That's why people in the southern hemisphere rely more on the Southern Cross, the Crux constellation, which, while not exactly aligned with the pole, is a lot easier to spot. So astronomers took this whole system and built an equatorial coordinate system. Instead of latitude and longitude, it uses right ascension and declination, a celestial grid projected onto the night sky. Imagine stretching Earth's equator and poles out to the stars. Now every star, galaxy, and nebula has an address. This system is rock solid for anything within our planetary backyard. It's how we aim telescopes, track satellites, and navigate across oceans. But the farther you zoom out, the more cracks start to show, because all of it still depends on the Earth. And once you leave it behind, the whole idea of orientation starts to fall apart. It would be so simple if the Earth was just flat, like ancient tribes thought. But the joke is, we can apply it to the whole solar system. It has what's called the ecliptic plane, and it's basically the flat, invisible sheet traced by Earth's orbit around the Sun. It's basically the solar system's version of the equator, the zero line, the baseline, the floor we build everything else on. And because the ecliptic came from the ancient Sun's protoplanetary disk, most of the planets, Mercury to Neptune, orbit the Sun along this same plane, which makes the ecliptic an incredibly handy reference for mapping the solar system. Still, there's a place for nuance. Contrary to what most people think, the planets aren't perfectly lined up like marbles on a flat table. They're tilted, each in its own slightly askew orbit. Venus is off by about 3 degrees, Mars by almost 2. But then you get the outliers. Take Mercury. Its orbital plane is tilted by about 7 degrees, making it one of the most skewed among the classic planets. And of course, we can't leave out Pluto, the X-planet with main character energy. Its orbit is tilted a whopping 17 degrees compared to the ecliptic. That's almost a diagonal. When Pluto was discovered in 1930, it was actually above the ecliptic plane, but because of its long eccentric orbit, it eventually dipped below the plane in 1989. It'll stay there until approximately 2113. That's over 120 years spent on the so-called underside of the solar system. Meanwhile, Voyager 1, the farthest human-made object from Earth, is currently cruising at about 35 degrees above the ecliptic. It's headed toward a constellation called Ophiuchus, which, fun fact, some people argue should be the 13th zodiac sign, but let's not open that can of worms. Voyager 2, it's taking the scenic route, about 48 degrees below the ecliptic, aimed at Telescopium, which, yes, is actually the name of a constellation and not just an IKEA lamp. And comets, they're the daredevils of the solar system. Take C2023A3, one of the more hyped comets in recent memory. It's swooping in from well above the ecliptic plane on a dramatic plunge toward the inner system. So this frame, the ecliptic, is great for anything happening within the solar system. So if you were lucky enough to wake up somewhere in the Sun's vicinity, just look for bright moving objects like Venus. Its motion will let you calculate your own position relative to the ecliptic. But once you zoom out, and I mean really zoom out, this whole plane becomes just another local quirk because the stars are dancing to a completely different beat. Welcome to the Milky Way. Our galaxy is a sprawling spiral of hundreds of billions of stars shaped like a flattened disk. And that disk gives us our next major reference point, the galactic plane along which all the stars orbit the galactic center, kind of like the ecliptic, but for the entire galaxy. If you Google the position of the solar system in the Milky Way, you'll find pictures like this. So, we're kinda on the left in this disk? Well, not at all. It's just the popular infographics convention to use that particular angle. But what about our vertical position relative to the disk? Fortunately, it's the same above and below. Only now we're talking in terms of light years. The Sun, and everything orbiting it, including you, is currently riding about 20 to 20 light years above the galactic midplane. That might sound like a lot, but considering the Milky Way is over 1,000 light years thick in places, we're basically skimming the surface. But wait, why do we see the Milky Way as a diagonal band across the night sky? Well, that's because the plane of our solar system, the ecliptic, is tilted about 60 degrees relative to the plane of the galaxy. So, when you look up on a clear night and see that dense, glowing stripe cutting diagonally across the sky, you're actually looking edge-on into the galactic disk, the thin slice where most of the stars are packed. And the actual movement of the solar system relative to the galaxy looks like this. Very messy. Could easily get a vertigo from one of these videos. To make sense of all of this to us, Earthlings, astronomers use galactic latitude and galactic longitude. 0 latitude means you're exactly in the galactic plane. Positive values mean above, negative means below. Kind of like elevation on a topographic map, but for stars. For example, M13, a globular cluster in Hercules, floats much higher, around 40 degrees above the plane. Meanwhile, mere 7 angular minutes down below the plane, you'll find the Milky Way's dark heart, Sagittarius, a star, the supermassive black hole anchoring our galaxy. And here's a fun twist. The Andromeda Galaxy, our looming galactic neighbor, appears high above us in the sky. But from the Milky Way's perspective, it's actually about 21 degrees below the galactic plane. So what we see as up is technically down in galactic terms. Oof! But if you think this is confusing, remember that even our galaxy is just one node in something enormous and chaotic. So when you zoom out one last time, direction gets weirder than ever. Enter the cosmic microwave background, or CMB. It's essentially a shell of the oldest light we can see in our observable universe, a faint glow left over from the Big Bang, now stretched into microwaves by 13.8 billion years of expansion. And CMB gives us something truly unique, a universal reference point, but not of direction, of motion. You see, if you were standing completely still relative to the CMB, no drifting, no spinning, no orbiting, then you'd see that ancient light as perfectly uniform in every direction, same temperature, same wavelength everywhere. But we are not standing still. The entire solar system is hurtling through space at roughly 370 kilometers per second relative to our universal reference point, and this motion creates a visible fingerprint in the CMB called dipole anisotropy, one side of the sky. The direction we're headed looks ever so slightly warmer because the light is compressed by our motion. The opposite side, cooler because we're moving away from it. It's like driving through rain. Even if the drops are falling straight down, they seem to hit your windshield from the front because you're moving. The universe is doing the same thing to us with photons instead of water. But wait. If the cosmic microwave background gives us the only true rest frame in the universe, you might be wondering, can we flip it around and treat it like a kind of cosmic globe? You know, slap some coordinates on it, draw an equator and say, hey look, that's CMB north, that's south, and we're right here. Tempting, but no. You see, the CMB isn't a map of space, but it's a map of motion through time. It's not a structure we're inside. It's a snapshot of the whole universe when it was just 380,000 years old. Every direction we look in the sky, we're seeing the same thing. Ancient light, stretched and cooled, arriving from every corner of the cosmos. There's no top or bottom baked into it. The only asymmetry in the whole thing is that dipole anisotropy, that temperature difference caused by our motion through space. So in the end, it's not we are here on some universal star map. It's more like we're moving this way through this sea of radiation. And even if you try to invent a coordinate system based on the dipole, say, call the direction we're headed CMB north and everything else relative to that, it wouldn't be stable because the solar system isn't coasting in a straight line. It's orbiting the galaxy, which is itself moving relative to the CMB with a totally different speed of 550 kilometers per second. So because of this mess, today's CMB North won't be the same in 100 million years. It's not a cosmic landmark. It's more like a speedometer that only works if you look backward, 13.8 billion years into the past. But almost everything about our universe on a really large scale comes with a twist, and so does CMB. We just stated that it's the same glow in every direction, except it's not so simple. Enter the axis of evil. Sounds like a comic book villain, but it's actually an anomaly found in the lowest multiples of the cosmic microwave background, the large-scale patterns in the CMB sky. To put in simply, there are certain temperature fluctuations in the CMB which should be randomly distributed, but instead are pointing roughly the same way. That shouldn't happen in a perfectly uniform directionless universe we imagine. And that's not the only red flag. In the constellation Eridanus, there's a region of the CMB known as the cold spot, noticeably cooler than surrounding areas. Some theories suggest it's caused by a supervoid, a massive underdense region of space that stretches for hundreds of millions of light years. Others have proposed more exotic ideas, like imprints from a parallel universe or a wrinkle in the fabric of cosmic inflation. In any case, if these patterns are real, they suggest the universe may have emergent directions, not baked into space itself, but arising from how matter and energy ended up distributed. In other words, up and down at the largest scale might not come from a grid or a map or a spin, but from the unevenness of cosmic structure. It's just buried so deep in the fabric of space that we're only now starting to see the outlines. In 2021, astronomers studying distant quasars suddenly discovered a true monstrosity. The Giant Ark, a sweeping curve of galaxies stretching over 3 billion light-years. That's not just huge, it's cosmologically impossible, or at least it should be. Standard cosmology assumes that no gravitationally connected structure should exceed 1.2 billion light-years. But as you can see, the Giant Ark is almost triple that, and it isn't the only outlier. Not long after, astronomers found the Big Ring, a 1.3 billion light-year loop of galaxies that seems to twist, maybe even rotate in space. That's not just a curiosity, that's a pattern. And in science, patterns demand explanation. Because if you start finding structures this big, and they're all pointing, curving, flowing in certain ways, then maybe direction in the universe does exist. Not a magnetic north, not an up or down, but a statistical orientation. Imagine overlaying all the Giant Ark's rings, walls, and filaments we found onto a single cosmic map. If those features cluster toward one side more than the other, or if their axes line up just a bit too well, that gives you a vector. And from that, a reference frame. That's how we use Earth's terrain to define direction here. Valleys, rivers, coastlines. The universe might not be so different after all. If matter flows along these megastructures like water down a slope, then their alignment could help us define a cosmic downhill. And it seems like we found the closest one already. Remember the Milky Way's relative CMB speed I mentioned earlier? The direction of this motion is not random. Back in the 80s, the astronomers found out that thousands more galaxies were rushing with us to the same point somewhere in the Centaurus constellation. Impressed, scientists named this mysterious structure the Great Attractor. That's some axis of evil vibes, but why so ominous? Simple, we just can't see what's there because of the Milky Way itself. Its wide band of stars and dust in the night sky obstructs the view for the most sensitive telescopes, so the true nature of the Great Attractor remains a mystery, and will remain for at least 100 million years while the solar system rotates to a better spot in the galactic disk. all we know for now, the Great Attractor is probably some enormous cluster of galaxies somewhere between 150 and 220 million light-years away. So our Earth, our solar system, and even the Milky Way itself are essentially sliding on a cosmic slope we're too small to recognize, surfing a gravitational current along with our entire galactic neighborhood. If so, maybe that is the kind of down direction in our universal neighborhood. Actually, our own Laniakea supercluster is defined by the Great Attractor in its center. Is it practical to consider this object a universal floor, though? Not so much. We've been looking for a flat plane or a North Pole, while the real answer is a drift, a tug towards something denser in the universe that looks not so uniform after all. So, in the end, outside Earth, above, below, north and south are still meaningless. And the most solid thing we have is just 100,000 galaxies caught in a slow, one-way current through the hidden valleys and ridges of the cosmic landscape. I'd leave it at that, if not one recent discovery that truly blew my mind. In 2025, astrophysicist Lior Shamir and his team published a study using data from the James Webb Space Telescope's Advanced Deep Extragalactic Survey, and what they possibly found is astounding. The study analyzed over 260 ancient spiral galaxies, and about two-thirds of them rotate clockwise from our point of view, while only a third counterclockwise. And this asymmetry is strong enough to suggest that something made these galaxies prefer one rotation over the other. If those patterns are real, and that's still a big if, then the universe could have a cosmic axis after all. The whole cosmos might be spinning just a tiny bit. So suddenly, up and down, north and south would start to mean something again if we find this axis and build coordinates around it, just like with Earth's rotation. This means we could really make a globe of the universe. And wouldn't that be something? These puny creatures that couldn't tell directions apart just outside their star cracked the orientation of the unimaginably vast cosmos. That would be sufficient enough grounds to start looking down on the universe, don't you think?